Hello everyone, and welcome. This is Tanvir, have experience working on New York City School Construction Authority projects. If you're involved in SCA work, whether as a design engineer, general contractor, mechanical contractor, HVAC manufacturer's representative, BMS agent, or commissioning professional, you already know how important it is to fully understand the HVAC design standards that guide these projects. This video is the start of a 4-part series dedicated to the SCA HVAC design requirements outlined in Section 6.2. We'll walk through the philosophy, system selection, design criteria, and detailed standards that shape every school project in the city. The goal of this series is to make the requirements clear and practical. If you're new to SCA work, you'll gain a strong foundation. If you've been doing it for years, this will serve as a valuable refresher. Either way, you'll walk away with insights that will make your project smoother and your coordination stronger. So let's get started with part 1 of this knowledgeable series. Before we dive into HVAC design requirements, let's take a quick look at the School Construction Authority, or SCA. The SCA is the organization that sets the design standards for building and rehabilitating New York City public schools. These standards are more than just checklists, they're a guide that architects, engineers, and consultants follow to make sure every school project meets a high level of quality and consistency. The standards are divided into 4 major groups. First, design requirements. These define the acceptable design practices, and often go beyond what the code itself demands. Second, standard specifications. These define the materials you're allowed to use in NYC public schools, and if you want to deviate from them, you need approval from the Deviations Committee. Third, standard details, the drawings that show exactly how systems and assemblies should be put together. And fourth, room planning standards, which guide how spaces are laid out and used. In addition to those, there are also supplemental guidelines like the NYC Green Schools Guide, procedural documents, and other resources for the design community. Consistency is a big theme in SCA projects. For example, all drawings prepared for the SCA have to use standard title sheets, and the preferred sheet size is 24.5 by 36.5 inches. In this presentation, we're going to focus on the design requirements for mechanical services, specifically HVAC systems in New York City schools. So with that context in mind, let's begin. 6.2.0 General Overview of HVAC System based on SCA. 1. The preferred HVAC standard is to use air source heat pumps. 2. Rooftop packaged DX heat pump units are the preferred choice for new construction and major modernization projects, due to its simpler controls, and rooftop packaged DX systems have historically lower construction costs compared to air-to-water heat pump chiller heater systems. 3. Energy modeling has shown that multi-zone variable air volume (MZVAV) systems using either custom MZVAV DX heat pump units or custom MZVAV air handlers served by chiller heater plants use the least amount of energy. 4. All heat pump systems must have a redundant emergency backup heating system that provides 75% of the heat pump's capacity. With DX units, this is achieved with simple electric resistance coils in the air handling units, which is a less complex solution than the electric boilers required for air-to-water systems. Key design requirements and components. 5. Air discharge and fans. Both DX and dual-temperature air handling units must have a nominal air discharge of 55 degrees Fahrenheit in cooling mode and be equipped with airfoil plenum or fan array supply and exhaust fans. 6. Filtration. DX heat pump units and dual-temperature air handling units must have pre-filters with a minimum MERV 8 rating and final filters with a minimum MERV 13 rating. Filters must be on both sides of any energy recovery wheel. 7. Refrigerant. Rooftop packaged DX heat pump systems are preferred over split VRF DX systems because they have factory packaged refrigerant lines, which minimizes the likelihood of leakage. 8. OEM controls are required for heat pump DX units and dual-temperature air handling units to simplify field commissioning and coordination. These controls must be native BACnet or have communication cards for integration into the standard DOE BACnet network. 9. Ventilation. Energy recovery wheels, ERW, and demand-controlled ventilation are generally required for all custom RTU units. There are specific exceptions, but they require approval from the authority's TSS unit and must be justified with energy modeling. 10. Perimeter heating. For spaces served by central DXMZ VAV heat pumps, electric baseboard units are required for perimeter heating in non-assembly areas like classrooms and offices. 11. Special spaces. Specific spaces like science labs, libraries, and music rooms, where shelving would interfere with baseboard heating, should use fan-powered VAV boxes with electric reheat coils when a central DX heat pump unit is utilized. Toilets and stairways should use electric or hot water cabinet heaters. 12. Condensing boilers. For existing systems requiring a gas burner retrofit or replacement, the condensing boiler must have a thermal efficiency of 88% at a 130 degrees Fahrenheit return water temperature. They must be equipped with an integral gas valve train T. 13. Safety. Condensing boilers must be arranged for single fuel operation with firm gas and use linkage-less burners. Gas meter rooms, if provided, must have explosion-proof exhaust fans, light fixtures, and other accessories. A gas leak detection and alarm system must also be provided. 14. The source energy target is currently 60 kBtu SF per year or below, though this may vary. Projects with a higher energy use intensity, AUE, in the high 60s must be discussed with the design and resiliency team. HVAC system selection criteria. Outlines various factors for selecting the appropriate HVAC system for different project types. 15. New construction, major modernization. Multi-zone variable air volume 510 heat pump units are the preferred choice for non-public assembly spaces like classrooms and offices. Public assembly spaces like gymnasiums and auditoriums should be served by custom single-zone variable air volume 510 heat pump units. 16. Existing buildings. The selection depends on several factors, including the age of the roof, building utilization rate, location of the mechanical equipment room, MER, structural floor-to-ceiling height, and window condition. For buildings with limited slab-to-slab heights, options like DX vertical unit ventilators, VUVs, or DOAS, VRF units are considered and VAV boxes are not an option. If the roof is over 15 years old, indoor units like vertical unit ventilators, VUVs, DOAS, or ERVs coupled with VRF or FCUs are preferred over rooftop units to avoid roof penetrations. If windows are single pane, more than 35 years old, or have a poor rating, BCAS 4 or 5, VUVs are a more appealing option as window replacement would be a part of the project anyway. Central systems are a better option if windows are narrow or limited. If a project is not bound to comply with the Green Schools Guide, sound pressure levels of 45 dBA, NC 40 are acceptable. 17. Carbon reduction. If existing boilers have less than 15 years of life, they should be replaced with heat pump systems. 18. For buildings with pitched roofs, indoor mechanical equipment rooms, MERs, are more optimal for central units. 19. In buildings with cinder concrete slabs, clay tile arches, supplemental steel is required, and lighter dual-temperature VUVs are preferred over heavier compressorized VUVs. 20. If existing chilled water piping is in good condition, dual-temperature chiller heaters become a more feasible option. 21. For auditoriums with ornate or historic ceilings, lower floor MER-located indoor central units are preferred to avoid overhead ductwork that would interfere with the ceilings. 22. For A2L refrigerant systems, continuous monitoring is required if a refrigerant leak could exceed the 25% lower flammability limit, LFL, in the event of a ventilation system failure. This may require area refrigerant leak detectors. 6.2.1. HVAC unit centralization and coordination. The primary goal is to centralize HVAC units as much as possible to minimize the total number of units. The initial architectural layout should be planned so that one unit can serve multiple spaces. 1. Public assembly, PA, spaces. Gymnasiums, gymatoriums, and auditoriums must each be served by a dedicated single-zone variable air volume, SCVAV, heat pump or dual-temperature air handling unit. The kitchen and cafeteria may be served by a single combination SCVAV unit. If a unit serving a gymnasium is also used for locker rooms, the air from the locker rooms cannot be recirculated, and the locker rooms must be negatively pressurized. 2. Non-assembly spaces. Corridors, classrooms, offices, and other non-assembly areas in new schools or major modifications should be served by multi-zone variable air volume (MZVAV) units. The same central unit can serve both the library and classrooms since they have the same occupancy class. These MZVAV units must provide tempered ventilation air in the heating season and all space cooling and ventilation in the cooling season. 3. Existing buildings. For existing buildings with ample ceiling height and an unaltered envelope, central VAV heat pump or dual temperature air handling units are recommended. 6.2.2. Ductwork and shafts. 1. To maximize floor space for instruction, the SCA prefers roof-mounted DX heat pump units. The ductwork from these units must have multiple supply and return risers within multiple 2-hour rated shafts. The horizontal distribution ductwork should be headered in the space above the top floor's suspended ceiling to allow for smaller ductwork on lower floors and shallower slab-to-slab heights. To support this, the top floor's slab-to-slab height can be up to 2 feet higher than other floors. 2. If this design results in very high external static pressure that would violate energy codes, the designer should consider placing split DX heat pump units or air handling units in mechanical equipment rooms located within the building. 6.2.3. Design approach of non-assembly spaces, classrooms, offices, corridors, etc. System type and application. 1. Apply to new construction, major modernizations, and capital improvement projects. 2. Classrooms, offices, and other non-assembly spaces must be served by custom multi-zone variable air volume (MZVAV), central recirculating DX heat pump or dual temperature hot water, chilled water AHUs. 3. Multi-zone VAV units handle ventilation air during heating season and provide all cooling capacity. 4. Distribution via VAV boxes with ceiling diffusers. 5. Acoustic performance requirement. 40 dBA. Noise criteria valued 35, maximum in classrooms, offices, achieved with non-fan powered VAV boxes. VAV boxes. 6. Each classroom, office must have a non-fan powered VAV box with integral sound attenuator. 7. Under low load, boxes throttle down supply air. 8. Acoustical lining downstream allowed only per DR 6.2.25, acoustical standards. Special classrooms, pre-K 2nd grade. 9. Classrooms with adjoining toilets may exhaust part of their outside air through the toilet exhaust fan. Ventilation and airflow scheduling. 10. Engineer of record must calculate a. Fully occupied minimum OA flow. b. Standby minimum OA flow, for DCV reset, circa maximum airflows per space. 11. Values must be shown on drawings in a ventilation schedule, including each VAV box's fully occupied min and max airflow. 12. Max airflow must meet thermal loads at the adjustable space temperature setpoint. Demand-controlled ventilation, DCV, 13. Required for each space, in addition to an energy recovery wheel, ERW, at the central AHU. 14. Outdoor air reset logic must comply with ASHRAE 15-2022 refrigerant charge, dispersal requirements. A. EDVC refrigerant charge calculations required. B. If A2L refrigerant circuit charge exceeds EDVC, minimum outdoor airflow cannot go below ASHRAE 15-2022 EQN 710 to ensure ventilation for leak dispersal. 15. Drawings must show appropriate minimum flows for ventilation plus refrigerant leak control. DCV logic. 16. During occupancy, detected by carbon dioxide sensor, A. Minimum OA equals space ventilation rate, CFM, SF times SF, plus occupant ventilation rate, CFM, person times instantaneous population. 17. During unoccupied, low occupancy, ventilation reduced to standby minimum, but not below ASHRAE safety minimums for refrigerant dispersal. 6.2.4. Design requirements for HVAC systems in public assembly spaces for schools, including auditoriums, gymnasiums, and cafeterias. The requirements vary based on the type of project. New schools and major modernizations project. 1. HVAC system. These projects must use custom single-zone variable air volume rooftop heat pump units or dual-temperature air handling units served by air-to-water chiller heaters. 2. Variable volume requirement. Variable volume units are required if the mechanical DX cooling capacity exceeds 65,000 BTU per hour or the fan horsepower of dual-temperature air handling units is over 1/4 of a horsepower, per ASHRAE standards. 3. Exceptions. Constant volume units may be used for historic buildings or for repairs where extensive revisions or insufficient space exists. However, more efficient systems are preferred if technically feasible to meet New York City's energy-saving mandates. 4. Preference. Heat pump units are preferred over dual-temperature air handling units. 5. Heating and cooling. SCAHVAC systems should provide ventilation air at 65 degrees Fahrenheit during heating, with terminal heating, such as electric or hot water convectors, in the PA spaces. Kitchens should have reheat electric or hot water coils. In cooling mode, units are coupled with a mixed variable air volume system. Capital improvement projects. 6. HVAC system. These projects must use commercial single-zone VAV rooftop heat pump units. 7. If a public assembly space can be divided into independent subspaces, multiple zone VAV heat pump or dual-temperature air handling units must be used instead of single-zone VAV units. Each subdivided space needs its own VAV box and temperature sensor. 8. Energy recovery wheel and demand-controlled ventilation are mandatory design features for units serving public assembly spaces, as indicated by SCA standards and building codes like ASHRAE 90.1 2016 and the 2020 NYC ECC. The purpose of an ERW is to recover energy from exhaust air, which helps to reduce the heating and cooling loads on the HVAC system. DCV system adjusts the amount of outside air delivered to a space based on the actual occupancy, typically by using CO2 sensors. By reducing the amount of outside air when the space is not fully occupied, DCV systems save significant energy. 6.2.6. The design requirements for HVAC convectors and enclosures. These requirements are applicable to new construction, major modernizations, and capital improvement projects. CIPs. Here are the key design approaches for different areas. 1. Corridors, stairway landings. A. Fully recessed electric convectors or electric cabinet heaters mounted 4 inches above the finished floor can be used. B. Alternatively, ceiling-hung, fully recessed electric cabinet heaters can be used. C. If space allows, electric baseboard units may also be installed. D. When dual-temperature air-to-water heat pump chiller heaters are used, the same types of units, convectors, cabinet heaters, or baseboards, can be used, but as hot water units instead of electric. E. In areas with frequently opening, closing doors, terminal units, door air curtains, cabinet unit heaters, convectors, must be supplied with a 30% propylene glycol water mixture from the primary dual-temperature water loop when chiller heaters are utilized. 2. Toilets. A. Toilets on the building's perimeter, top floor, or on a slab on grade must have terminal heating capacity. B. Fully recessed ceiling-mounted electric cabinet heaters are to be used. Circa. In applications with heat pump units that generate hot water, fully recessed ceiling-mounted hot water cabinet heaters or fully recessed hot water convectors, mounted 4 inches above the finished floor, may be used. 3. Public assembly spaces. A. These spaces, when equipped with single-zone variable air volume (SCVAV) units, should be served by recessed perimeter electric convectors mounted 4 inches above the finished floor. B. If chiller heaters are provided, recessed perimeter hot water convectors should be used instead. 4. Kitchens. A. Floor-mounted heating units are not permitted in kitchens. B. Terminal heating must be provided by an electric heater or a hot water coil located in the duct serving the kitchen. 6.2.7. The design requirements corridors HVAC unit according to SCA HVAC for new construction and major modifications. In new construction and major modification projects with adequate ceiling heights, corridors should be served by either 1. Custom multi-zone classroom variable air volume heat pump units. 2. Classroom dual-temperature multi-zone VAV air handling units that are served by air-to-water heat pump chiller heater systems. The use of these systems is subject to SCA review and approval during the early design phases. A. For top-floor corridors with a cooling load, variable air volume (VAV) boxes are required. These VAV boxes must be controlled by temperature sensors in the most remote parts of the corridors. The minimum setting for these VAV boxes must never be less than 0.06 CFM SF, as per the 2022 NYC Mechanical Code, Table MC 403.3.1.1. Additionally, the setting must maintain a transfer of air from the corridor to adjacent toilets and electrical closets. For core corridors without significant loads, constant air volume boxes can be used, with the flow set to the greater of 0.06 CFM, SF or the air transfer requirements. B. For terminal heating, options such as electric baseboard or hot water fin tube radiation may be needed in certain locations, like top floor or slab on grade corridors, or those over unheated basements. Other options for heating include fully recessed wall-mounted convectors or recessed cabinet unit heaters. HVAC for existing buildings with limited ceiling heights. In major modification or substantial reconstruction projects in existing buildings where classrooms have limited ceiling heights, different systems are used. 1. If classrooms are served by DX vertical unit ventilators or VRF units and decoupled custom DX-DOAS central heat pump units, corridors should have a dedicated DX multiple zone variable air volume system or a dedicated single zone constant air volume unit. 2. A key restriction is that split A1 or A2L refrigerant piping is not allowed in corridors, as systems with this piping are not considered unit systems under Section 7.5.1.2 of ASHRAE 15/2022. A unit system is defined as a self-contained packaged system. HVAC for capital improvement projects, CIP. 1. When upgrading HVAC systems for corridors in a CIP, the same systems as those for capacity projects, described in Sections A and B, should be used. Using air-to-water heat pump chiller heaters requires approval from the SCA after a review of the CIP pre-scope electrification report. Corridor exhaust. 1. For all projects, capacity or CIP, outside air supplied to the corridors must be exhausted by the toilet and janitor's closet exhaust fans. The outside air can also be exhausted by the combined central classroom, corridor multi-zone variable air volume, MZVAV, heat pump units or dual-temperature MZVAV units in new schools and major modifications. The toilet and janitor's closet exhaust systems may be combined. 2. Additionally, in projects where classrooms are served by VAV boxes or other specific systems, all classroom exhaust air must be returned to the central unit to enable the use of total enthalpy energy recovery wheels, which recover both sensible and latent energy. 6.2.8. Wardrobe/locker ventilation in SCA project. Design approach. 1. Mechanical exhaust ventilation is not required for wardrobe closets and/or locker areas in classrooms and corridors. 2. Wardrobe closets inside each primary school and intermediate school classroom shall be provided with bottom louvers to provide natural ventilation. 3. Corridor lockers shall be provided with top and bottom louvers for natural ventilation. 6.2.9. Heating and cooling design parameters for load calculation systems must be designed in accordance with several standards, including Section MC 312 of the 2022 NYC Mechanical Code, ANSI, ASHRAE, ACCA 183/2007, and ASHRAE 90.1/2019. When energy recovery systems are used, heating and cooling loads need to be adjusted to account for the resulting load reductions, as per Section C403.1.1 of the 2020 New York City Energy Conservation Code, NYCECC, Heating. Design parameters. Heating design parameters for new construction, major modifications, and CIPs must follow specific criteria. Ventilation and occupancy. 1. Natural ventilation alone, without the use of fans, is not permitted. 2. All occupable spaces must be either naturally ventilated and mechanically exhausted, or mechanically ventilated. Spaces with air conditioning must be mechanically ventilated. 3. Ventilation occupancy is determined by the lower value between the UFT contract student occupancy, plus staff, and the egress occupant density from Table BC 3 January 1004. The default occupant densities from Table MC 403.3.1.1 are not to be used, but the ventilation must be checked to ensure it's above this minimum. 4. For typical classrooms, the UFT student maximum occupancy will usually govern. The UFT contract student occupancies are: A. Pre-K and K, 27 students. B. PS, is grades 1-8 33 students. C. HS grades 9-12 34 students. 5. DCV, demand-controlled ventilation. A. Only modulates outdoor air intake at the unit. B. Total supply air must never fall below fully occupied outdoor air requirement. 6. For smaller rooms and for spaces without a defined student occupancy, like administrative spaces, ventilation occupancy is based on the default occupant density from Table BC 3 January 1004, egress occupant density. 7. The minimum central unit outdoor air intake ventilation rate for vacant public address, PA, spaces, such as auditoriums or gymnasiums, is the space's square footage multiplied by the CFM per square foot requirements defined in Table MC 403.3.1.1. This minimum rate maintains indoor air quality by accounting for off-gassing from materials like carpets and paints. 8. Cafeteria, kitchen combination units. Vacant cafeterias must maintain ventilation for kitchen exhaust makeup, general, toilet, can wash exhaust. 9. For dual-function spaces like a gymatorium, outdoor air ventilation rates must be calculated for each mode of operation: gym use, auditorium, assembly. 10. A2L refrigerant impact. A. If charge exceeds EDVC, ASHRAE 15-2022. EQ. 7-8. OA flow must also satisfy EQ. 7-10 to disperse leaked refrigerant. B. If below EDVC, based solely on occupancy ventilation rates. 11. Design and load calculations. A. Calculations are based on the net floor area. B. The inside ambient design temperature, room temp, is 72 ring operator FDB. C. The outside heating design ambient temperature is 12.8 ring operator F with 99.6% weather data for NY Kennedy Airport. 12. Heating load components must include: A. Envelope transmission losses. B. Ventilation air load. Circa. Basement floor losses. D. Infiltration losses, pressurization effects. E. System inefficiencies, duct leakage, damper leakage, piping, duct wall conduction. 13. Cooling design parameters. Cooling requirements for new construction, major modifications, and capital improvement projects follow a separate set of criteria. 14. Ventilation and occupancy. A. The fresh air requirements for all spaces are the same as those for heating. B. Variable air volume, VAV, systems, which are the current SCA standard, must use carbon dioxide, CO2, sensors to adjust the minimum outdoor air ventilation airflow. 15. Design and load calculations. Similar to heating, calculations are based on the net floor area. 16. Design conditions. A. Inside, 78 degrees Fahrenheit dB. B. Outside, 89 degrees Fahrenheit dB, max. C. Cooling tower, 78 degrees Fahrenheit WB, if used. D. VAV case, standard, E. Carbon dioxide sensors reset minimum central OA per paragraph 8.3. 17. Cooling load components. A. Solar plus envelope transmission. B. Ventilation loads. Circa. Sensible plus latent gains. Per occupancy. D. Internal heat gains, lighting, equipment, watt per soiree FEF. E. Infiltration, with pressurization, F. Fan heat. G. piping, duct heat transfer, leakage, inefficiencies.